All right, so yesterday I also gave you guys while you were taking a quiz this packet of questions uh, related to harmonic motion. Right now, this was just in case you finished the quiz like 5 minutes early. Some of you guys did. They can start going through those. So we're going to go through the answers to these questions. So let me put my screen over. Okay. And throw these questions up here. Okay. All right. So if you had that paper from yesterday, then whoops. Then you can go over it along with me here. But okay. All right, so yeah, okay. Number one, a student wishes to determine the unknown spring constant of a particular spring. Okay, so how stiff is the spring? Okay, now pause right there because there's two main formulas that involve a spring constant, right? There's Hooke's law, F equals kx. Okay, now that doesn't have to do with anything being in motion. That could just be maybe like a block hanging at rest on a spring, for example. F equals kx, right? And the other one is time period is 2 pi square root m over k, right? So you put a, say, bob on a spring, you pull it back and let it bow, wow, wow, oscillate. Okay. The student attaches various masses to the spring and measures the time period capital T of a simple harmonic motion. The results, the student then plots the graph of the square of the time period as a function of the mass on the spring. What is the spring constant? Okay. Ooh, that should be something you should be able to do too, is if you get all the masses, so you're switching out the mass, right? So you do little masses, medium masses, big masses, and then you measure the time periods. Okay? You should be able to linearize the data, like create that graph from scratch too. So let's do, let's answer that first, and then we'll look at linearization. Okay. And so you guys figure out what's the answer to that question. Give you guys a minute there. All right, I've got the answer. He needs a little bit more time. He needs a little bit more time. All right. So let me see. Show of hands. How many guys got option A? Option A. Who got option B? Who got C? And who got D? Ooh, 1, 2, 3, 4, 5, 6. 6 guys. All right. Yeah, you guys are right. So it's 100 newtons per meter. Oh, so switch back over here. Okay. So I got this solution started here. Right, you're going to start from this periodic motion formula, right? So the time period of oscillating back and forth. Okay. So we got set up something like this. We got the mass on a spring, right? Pull it back, let go. It's go. Wow, wow, wow. Okay. So how much time it is? Okay. It's 2 pi times this mass. Okay. 2 pi times the square root of this mass divided by the spring constant. Okay. The question is, what is the spring constant? Okay. So something to do with the graph. Okay. Oh, now they said they were graphing time squared versus the mass, right? So it was variable mass, right? Hanging on different masses, right? Right. So hey, maybe that's a hint that you want to square both sides, right? Now, if you do that, that gets rid of the square root. So yeah, it's probably a good idea, right? And then if you take this k and you slide it over, ooh, look at this. You got t squared versus m. Isn't this like your y axis? And this is like your x axis of that exact graph that they just made, right? Now that should be something that you should be able to do like from scratch with just blank paper and maybe some data. You should be able to come up with that. Okay? But that leads exactly to what they were showing, because they have time squared and square seconds on this axis, and they have mass in kilograms on this axis, right? And then yes, there was there was this straight line where at one point they had a mass of 5 kilograms that corresponded to a time period of square time period of 2 square seconds, right? Like this was a point on the graph, right? And then it was a direct relationship. Right? So maybe they were doing lots of different masses and getting lots of different time periods and squaring the time periods, and it was something like that, right? Okay. So you could do here. Right? So the slope of this line is this relationship right here, right? That expression right there. 2 pi quantity squared over k, right? Isn't that what that would be? Right? And that's equal to, in this case, 2 over 5, right? And then the units, right? Square seconds over kilograms. Okay. So let's do that. Let's do 2 pi quantity squared over k is equal to 2 over 5. And that was like square seconds over kilograms. Okay. So see, I could cross multiply the k and take the 2 or 5 and multiply it the other way. Okay? So k is equal to 2 pi 20 squared times 5 on 2. Okay? And then the kilogram per square second, which is same thing as Newton per meter, right? Newton per meter. Okay. So those all in the calculator. 2 pi quantity squared times 5 on 2. Okay. Getting k is 98.7 Newton per meter. Okay. Now, this is an NMSI document, so not officially from AP, but they ask a lot of questions that are really close to what AP would ask. And AP likes to do is they like to round a little bit, plus or minus a little bit. Okay. Guys, good there? Right. Back over here. Right, number 2. Object attached to a spring oscillates horizontally without losing mechanical energy. Right? So maybe like a frictional surface. Kinetic energy versus time for the object is shown. Ooh, right? So there's either positive kinetic energy or there's zero kinetic energy. Hey, can kinetic energy go negative? Correct, it cannot, right? So 1/2 mv squared. Well, mass is going to be positive, v squared is going to be positive. It's a scalar value. Yeah, so kinetic energy can only be positive, right? Okay, so that makes sense. Which of the following could be the displacement versus time for the same object over the same interval? It could be, right? Right. Get a good look at those, run different scenarios in your mind, maybe jot some stuff down on paper. Kind of figure out what the answer to that one's going to be. All right, let me see, show hands what you guys came up with. Who thinks option A? Who thinks option A? Who thinks option B? Who says C? Who says D? Ooh, I see a bunch of hands for D. Yeah, that's it. That's it. It's gonna be D. Right. So let's switch over and see why that's going to be the case. Okay. Now they started their graph at time zero with a bunch of kinetic energy. Okay. So if that's true, if they started at a place where it would have a bunch of kinetic energy, that means it would be in motion really fast, right? Okay. So where would this be? So it's going back and forth, right? Okay. Does it start off at time zero at one of the endpoints or near the middle? Yeah, it has to be near the middle, just when they started recording the time, right? Because it was in motion moving really fast, right? So it has a huge kinetic energy there. But that would have to correspond with zero displacement from, well, at least from the equilibrium point, right? Now I'm going to put a point here. Now it's possible sometimes you could actually have like maybe you're measuring it from position zero could be here. And then you'd have to put the dot way up here and then it would oscillate about that point. That's also possible. The answer they went with happened to, it looks like, have the zero mark aligned with the equilibrium point. So I'll go ahead and just start there too. Although they didn't have to do that. They could have had it oscillate up here too. That's okay. Or even down here for that matter. Right, so I still want to see how these curves match up there. Right, so this thing is in motion, right? Like in the middle here. Let's say give it a take to the right, for example. Right. Let's say it goes out here. Right. As it goes out further, is it speeding up or slowing down? Well, it's slowing down, right? Or another way you can think is that energy is converting from kinetic to where is the energy going? It's going into the spring potential, right? Right. So, let's say hit like an X max, right? And some X max out here after some time, right? When it is out here at X max, right, how much kinetic energy? Zero. So this would have to correspond with like zero kinetic energy, right? And then it's going to come back through the equilibrium point, right? So that would be like right here. Well, interval time, right? Oh, but now it's moving really fast, just the other way, right? Now it's just going to the left, which now it's back at maximum kinetic energy again, isn't it? So now we're like back up here, right? Right, and then let's look at like maximum compression. So some time later, it'll be over here. So that'd be like maximum compression, like right there, right? Right. And then, we're at zero kinetic energy again. Right? So that would be like right here. Right? And then it'll go back and to the equilibrium point, and now we're back at maximum kinetic energy because it's moving really fast. So here's displacement versus time. And here's the kinetic energy versus time. Okay, so like that. Which is, I'll let you guys figure that out. All right, number 3, consider a simple pendulum time period, capital T, when on the Earth. What is the new time period of the pendulum if it's taken to a planet that has 16 times the mass and 36 times the radius of Earth? Right? It's a few little things you have to do to a possible simplification if it helps. You could make time period 1 second if you like, and then figure out what's the time going to be on this thing, right? Here, I'll help you guys out a little bit because there's a middle step you have to do. So 16 times the mass and 36 times the radius. If we're talking about a pendulum swinging back and forth, that's going to affect that's going to affect the time period of the pendulum. There you go, gravitational acceleration, right? The gravity field of the planet. Right? Okay, so first thing you have to do is figure out what is the gravity field of the planet, or at least what it is in proportion to like the base planet, which is Earth, right? Okay. And what is that formula? Lowercase g equals what? GM over r squared. Yeah, GM over r squared. Right, so that, okay. Here, let me jot that down on paper. So I'm saying the gravity field of the planet is capital G gravity constant times the mass of the planet divided by the radial size of the planet squared. Right? Right. So that, and we're interested in the time period of a pendulum is 2 pi square root L over G. Ooh, that G, right? Okay. All right, so switch back over here. All right, you guys figure out what is the new time period? Um, um, he needs more time. He needs more time. Oh, all right, all right. See how you guys did. And so show hands. How many guys got option A, option B, option C, and option D? All right. I saw a few hands for option B, and that's what I got. So switch over and you guys, I saw that. But where did I just, oh, let me pause this here. Pause. Right, so, here we go. We got time period of a pendulum, right? 2 pi squared over G. Now put a little subscript E, say like Earth, right? And then you had to do this as a middle step. You had to figure out, well, what is the gravity field of the new planet, at least compared to Earth? And I said 16 times the mass, but 36 times the radius. But don't forget the radius is being squared. So this comes out to 16 over 1296. 36 squared is 1296, right? And that reduces to 1 over 81, right? Helpful to have a calculator with that. So I can say the gravity field of this new planet is 1 over 81 gravity field of Earth. Wait, is that really strong or really weak? That's extremely weak. Oh, guys, if you went to, let's say you just go to the moon, right? You pull out a pendulum on the moon, right? Because on Earth, here's what a pendulum looks like on Earth, right? On the moon, would this be like, or this like, what do you guys think on the moon?
Maybe a lot slower.
Yeah, a lot slower, right? That's a much larger time period. So on this crazy planet that has hardly any gravity at all, it's got to be huge or a very small time period. Yeah, tiny. Yeah, I got backwards with it. Yeah, right. So large time period, right? Maybe a low frequency, right? Yeah, large time period. Has to be a huge time period, right? That could already probably like knock out two of the answer choices. Right, but let's run the math on this. So you got time period on planet X, I'll call it, is 2 pi square root L over G, but the G on this planet is 1 over 81 of what it is on Earth. Right? Right, now 1 over 81 in the denominator, well, you can just pull the 81 to the numerator, and it's inside the square root, so square root of 81 is 9. So the time period is 9 times what it would be on Earth. So 9 times the time period. So if it takes 1 second to swing back and forth on Earth, the same period, same pendulum would take 9 seconds to swing back and forth on that planet. That's good. So you guys can do that. Should be able to do that. All right, back over here. Number 4. Mass hangs vertically from a spring, so the spring stretches the spring distance x from its natural length, and the spring mass system has time period t when set into oscillation. The spring mass system, interesting, they're leaving out the Earth. Just I thought is set on an incline as shown. Right now, it's on a little wheel, so looks like we don't have to worry about friction. And the mass attached to the wheels. Oh, there we go. Frictionless bearings. When on the incline, how do the new spring stretch and oscillation compared to X and T? And so let's use one at a time. Actually, I'll start with oscillation period. Okay. So were you guys thinking for oscillation period, we're looking at time period equals 2 pi square root m over k, right? Square root m over k, right? And from the left picture to the right picture, what changes in that formula? Uh, okay, yeah, okay, well, in that particular oscillation formula, see that the mass doesn't change, the spring constant doesn't change, so nothing changes in the oscillation formula, right? Right, t 2 pi squared m over k. So I'm thinking just based on that, that the answer has to be either B or D, right? Either B or D, right? Okay. Okay. Now, if you're thinking about spring stretch, that could probably be Hooke's law, right? F equals kx. That's probably what they're thinking. Okay. And that might be different. Because I'm thinking the left picture, we're getting the full weight of the block, mg. And the one on the right, it should be what the sine component, I think, of this angle. Okay, sine component. So, or another way to think of it is, let's take things to extremes. What if this angle right here was like 0 degrees or approaching 0 degrees, right? So that this was like horizontal or almost horizontal, right? And you just let it go. Would it hardly stretch at all? No, if it was entirely horizontal, it wouldn't stretch at all, right? So I'm thinking from that point of view, the one on the left is going to stretch more, right? So, so that means the one on the right would stretch less. So I think the answer's got to be B. Let me check my answer on that answer key. What first answer key? Yeah, it's B. Right, and for that reason. Okay, so Hooke's law for how much it stretches and the time period of oscillation for that. Okay. All right. 5 and 6. Ooh, student performs an experiment involving spring hanging vertically from a stand. The student hangs a massless hanger on the spring and sets a motion detector underneath. Oh, motion detector down here, right? The motion detector measures distance to the bottom hanger to be 1 meter. The student then hangs 16 kilograms and sets it into oscillation. The position of the bottom of the hanger is shown as a function of time by the motion detector. Question 5, what is the spring constant? And question 6, during which these time intervals is the weight on the force, is the weight force on the mass greater than the spring force on the mass? Right, so first question first, what is the spring constant? What is the spring constant? Right. You guys saw that? I'll solve it. Do it again. All right. Show of hands. How many guys got A? Who got A? Who got B? Who got C? And who got D? Hmm. Okay, so I saw a few hands go up for option C, and that's what I got. I solved it two different ways and got same answer for both of those. So let's start with the oscillation, since that's the unit 6 perspective. Right? Now, oscillation, you can do time period equals 2 pi square root m over k. Right? Guys, what is the time period?
1.6 seconds.
Yes, 1.6 seconds. Right? Oh, that's here. If you go crest to crest, right? Crest to crest could be like that unit of time would be one time period, right? That's like from 0.4 seconds to 2 seconds. That is a 1.6 second time interval, isn't it? Is it? Or you could go from here to here, like one full S shape. Right? It's still 1.6 seconds. Right? All right, so we have 1.6 seconds. We got 16 kilograms as the mass. Right? You guys see all that? So let me switch over and you guys had it from here. So here's the setup. Right? Plug in what you know. We got 1.6 seconds here. We got 16 kilograms here. And then the rest of that is just algebra. So I can divide over the 2 pi. 1.6 divided by open parenthesis 2 pi. Okay, that's that. Square both sides. Okay, so now I'm looking at, okay, so raise that. Okay. Here, I'll write this down. 0.0648, so it's not a bunch of units, is equal to 16 kilograms divided by k. Or you could have done this different ways. I think they gave you 16 as a perfect square, so you could different ways you could approach it. Cross multiply k, divide this number down. K is equal to 16 over 0.0648. And we have to come out to newtons per meter if I kept my units and blah, 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 right? Use this as square seconds. That's what that would be. Right. And then, oh, what is that then? What is 16 divided by that? 246.7. K is 246.7 Newton per meter. They had an answer choice that said 250, which would be with an experimental error. Yeah, so it have to be 250 Newton per meter. I guess that. There was another way I did this too that also showed the same result. So let me flip back over because you could have actually solved this through Hooke's law. Hooke's law. Right? Hooke's law F equals kx. Right? Remember where was it here? They said about this 1 meter. So they said this was originally a 1 meter difference. Oh, can I say 1 meter? Okay. But then when they put out 16 kilograms, ooh, guys, what is the equilibrium value for this oscillation? Yes, 0.36. So it came all the way down to 0.36, and then it was oscillating around the 0.36 meter mark. Right? Ooh, so what's that difference? Is that too early to subtract? What's 100 minus 36? I'm getting 64 centimeters, right? So, okay, call it 0.64 meters. Okay, so if you let it like eventually come to rest, it would be at it would have stretched 0.64 meters, 0.64 meters. Okay, so let me flip back over and let's solve this with just plain Hooke's law. Right. So again, you know what the answer is already from oscillation. But, okay. Right, so here's free body diagram. Got weight down, spring force up. Okay. The sum of forces is 0. That's the framework for equilibrium from forces. So now we're back to unit 2, right? Like dynamics. Okay. So that force up, that force down have to zero out, right? So then I can shuffle this over and get that, right? Let's say you're solving for k. Well, here's it in terms of variables. Okay. We got mass of 16 kilograms, gravity field 10 meters per second squared. X is 0.64 meters, right? That's where you subtracted, right? And then you get 215 Newton per meter. Okay. Okay, you guys get there? Nice. There's 2 different ways to do that. Number 6. Which of these time intervals is the weight of the force on the mass greater than the spring force? Okay. So the weight should be constant, right? Like gravity force is pretty well constant. But the spring force pulling up, well, that's going to vary, right? Sometimes it's stretching a lot, sometimes it's not stretching very much at all. Like I bet when the spring is when the mass is all the way at the top, it's very small spring force, right? When it's all the way at the bottom, but there's a huge spring force. Okay. So can you guys look at this graph and figure out what time interval is the spring force? Or wait, which way did word this? So is the weight greater than the spring force? Okay. When is the weight down pulling more than the spring force up? Sure. Walk you guys through this one sort of. There's probably different approaches you could do for this, right? But the connection here between dynamics and kinematics. What one variable is the connection between kinematic motion and dynamics? What kinematic variable? Is it position, velocity, or acceleration? Acceleration. Because acceleration could be a rate change of motion, but it could also be caused by a force. So that's like the bridge between those two sections, right? Okay. So let's think in terms of that. At least this is how I would think of it. Okay. So half of you guys are in calculus. If you're in calculus, you know the connection on position versus time versus acceleration versus time. That's what property?
Derivative.
You have two derivatives, right? That's like concavity, right? Like concavity, right? So do you guys see here, this section here where it's like concave down versus this section here where it's like concave up? Where it's concave down, that means the net force has to be like downward. Where it's concave up, that means it's accelerating up, so the net force must be upward, right? Oh, well, net force downward means that weight is greater than the spring force. And net force upward means that the spring force is pulling up more than the weight is pulling down, right? That's one way to think of it. Okay? And then here, this point right here, you call that an inflection point, right? Inflection point, right? That's where it's going constant velocity just for one moment. And that's where the forces are in equilibrium. Okay? Okay, so if we're looking for the weight to be greater than the spring force, I'm thinking this section right here, right? This section right here. So that's from 0 to 0.8 seconds. Okay, and then also later on down here, that shows up. Right? But 0 to 0.8 seconds, I think would be a good, good answer choice. Okay, it looks like option A. Let me make sure the answer is A. Yeah, it's A. Okay. Guys got there? Number 7. Which of the following explains why a pendulum undergoing large amplitude oscillations does not exhibit a simple harmonic motion? So this is one of those details that's shown up a few times in FRQs. You guys have seen this in a few FRQs with pendulums, which is they say to only pull it back to like 15 or 20 degrees or to specify there. Sometimes they'll award a point. They say like experimental design, so have something to do with the pendulum. They're looking for, and they would give you a point if you say you don't pull it back more than like 20 degrees from the vertical, right? And so what if you went to like 45 degrees? Maybe that whole t equals 2 pi square root L over G maybe starts to get a little wonky and doesn't work exactly. Right? And so why would that be? Let's go through these one by one and see what looks like the best answer. The period of the pendulum does not depend on its mass. Okay, well, that's kind of true anyway, but as long as the mass is all concentrated in the bob, I don't think it really has to do with the angle you pull it out, though. That's probably not the best answer. The restoring force is not directly proportional to displacement. That might be what they're looking for. I don't actually know, but let's put a pin on that one. Right, the tension force is always perpendicular to the motion of the bob. Right, now that's closer to being true when it is at those small angles. So that would be less and less true the more you pull it away from the vertical. The mechanical energy of the bob remains constant. Well, of the bob Earth system, that would be true, but the bob itself, the kinetic energy is all going wacky. So that would not be true. That wouldn't be true anyway. Right. I'm kind of looking at B. Let me see if yeah, okay. So I'm looking at the answer key. They're saying the answer is B. All right, and here's their justification. They say if the restoring force for large amplitudes is proportional to sine theta, but simple harmonic motion requires the restoring force to be proportional to just theta. Okay. There's something called a small angle theorem, which says that sine of theta is approximately equal to theta for small angles. Now, it's only true if you're working in radians, right? So if you have an angle of like 5 degrees or less, like, and let's say you convert that to radians, and you plug in your calculator. Here, let me prove this to you guys. I want to show you guys something cool. Right. So let's switch the screen. Okay. So this is kind of related to draw this up. So they're talking about this pendulum swinging back and forth, swing, swing, swing. Right. We're thinking about this angle here, and ideally you want this angle to be not too big. So they say like usually it goes with like less than 20 degrees about. Right. And there's something called the small angle theorem. Or at least that's what I remember it being called, right? Which is that for small angles specifically, let's say like under 5 degrees or so, right? Sine theta is approximately equal to theta, and this is radians only, right? As long as you're working in radians, right? So let's take like 5 degrees, for example, 5 degrees. Okay, let's convert that to radians. How do you convert from degrees to radians?
Times pi over 180.
There you go, times pi over 180, right? Or I could say times 2 pi over 360, same thing. Right? So I'm getting like that many radians, right? Okay, you guys see like, let's call it 0.09. Is that okay? Like 0.09, right? So maybe slightly larger than 5 degrees, like 0.09. Right? What if I do, let me switch my, oh, I haven't done this in forever. Wait, how do I switch from degrees to radians? Oh, here it is, DRG. Okay, let me switch to radians. Okay, and let me put in what sine of 0.09. I bet the answer is going to be approximately 0.09. Okay, let's see how close it is. Oh, it is. Look at that. Sine of 0.09 is approximately 0.09. As long as you're working in radians. See, I switched to radians. Okay, let me switch back to degrees, which we usually use for this class. Okay, and so it's related to motion of pendulum. Okay. So yeah, so if you pull back to like 45 degrees, right, now think about the components of the forces, and it works out a little bit different. Number 8. Ooh, we got position versus time, and yep, that looks like a nice sine curve right there. The graph shows displacement as a function of time for a simple harmonic oscillator. The vertical axis is in terms of maximum displacement, capital A, which of the following graphs best represents kinetic energy and potential energy of the oscillator at 1.5 seconds. Okay. So 1.5 seconds. All right, let's go to that point. Bam, that's right there, right? 1.5 seconds. Ooh, do you guys see that that happens to align with exactly half the amplitude? Right? Right, so let me switch my screen over. We're gonna figure out the answer and then find the answer choice that would align with that. Right? So I know that the total energy is constant, and that's a combination of kinetic energy and potential energy, right? So like that. So here you have like a mass on a spring, for example, right? It's moving back and forth. Okay. And when it's going through the equilibrium point, it's all kinetic. And when it's at the extremes, it would have zero speed. So zero kinetic would be all spring potential, right? Maybe we'll call it spring potential, right? True. Right. So what about when it has an amplitude that's like halfway? Okay. Well, I'm thinking about the spring potential here. Let's write down the formulas for these. Okay, we've got your 1/2 mv squared here, okay. But you have a 1/2 kx squared here. And this x can go up to a maximum value of capital A, amplitude. Sometimes you see like capital A here for amplitude, okay, but that would be like maximum value. Okay. Right. So if x is half of A, guess what is a factor of 1/2 squared? It'd be a quarter, wouldn't it? So here, if the spring can, let's get some back. If this can go all the way to here, like maximum, but now it's only like halfway to that point, right? Halfway to that point, okay. Then the spring is only compressed half of what it could be, you know, for that particular oscillation. So the amount of energy here is a quarter of what it could be at a maximum, right? Right? So the energy would be back to here. It would have to be 3/4 would have to be in the kinetic energy, and the other 1/4 would have to be in the potential energy, right? So it'd be like here we got a 3/4 of the energy here, and the other 1/4 of the total energy would have to be in here, right? Because 1/2 squared is 1/4, so it have to be a quarter weight, right? So we'll have 3 times the kinetic compared to the potential at the halfway point. Okay. Let's see what aligns with that. Okay. Ooh. So which answer choice is that? It looks like B, doesn't it? Option B. All right, let me sure. Yeah, the answer is B. Okay. Right through there. B. Number 9. Diagram shows that a ball connected to yeah, right. This one has to do like putting a charge and what happens when they put on the charge. They kind of skip this one. Right. They're saying this one is the charge pendulum, right, where there's some kind of like electrostatic pull, right? The time period would be less because the storing force is increased. Okay. So if you like charge these like positive, negative, then they'll actually swing back and forth faster. Okay. They cut all that from the AP exam, so let's skip that one. Okay. Oh, number 10, mark 2 answers. Student measures motion of a spring mass oscillator and calculates a regression equation based on the oscillator's motion. That equation is 0.1 cosine 5.4 t. Okay? So here's the amplitude, 0.1 meters. That's about 10 centimeters. That is 10 centimeters, right? Okay. Right. Cosine, because if you pull it from equilibrium point and you start the clock there, then it'll be a cosine curve. Okay. And then this 5.4 is equal to 2 pi times the frequency. I need to go over that with you guys. I think I'll do it tomorrow. I'll show you guys oscillation graphs to part of the review. Right. And so the larger the value this is, the shorter the time period is going to be. Or the student takes down the amplitude and angular frequency from this equation. Which of the following can the student calculate from these 2 values? Well, the amplitude is this 0.1 meters. 5.4 is the angular frequency, right? So that's in hertz, right? Angular frequency is 2 pi times the regular frequency. What can you calculate? Can you get the period of oscillation? Yes. Here, I'll show you guys how you get the period of oscillation. So switch over here. So X is equal to X max, or the amplitude, times, I'll do a cosine. You can do sine or cosine, right? Of angular frequency times time. Time is a variable. Okay. Now, this omega is not angular velocity. It represents angular frequency. So it's different than what we normally do. Okay. Maybe this is a better way to think of it. It's 2 pi times the regular frequency times time is a variable. Okay. Or if you like, you can even do this. A times cosine, A is amplitude. Okay. 2 pi divided by time period times the time is an independent variable. Okay. Okay, so can you get the time period from knowing that this whole thing is like 5.4 hertz? Yeah, you can't get the time period. Guess that. Right. Here, since we're about to run out of time, you said the other answer is option D, the fastest speed obtained by the oscillating object. Okay, so probably like a conservation of energy that way. All right, I will see you guys tomorrow.